Right, hello. The reason I've picked on this integral particularly is that a couple of years ago back it caused quite a few problems for students on a A-level further maths exam. And the problem, this particular question they had to do two separate integrals, and unless they did both of them, they didn't actually get any marks. So in that sense, they missed out. If they couldn't do the tan squared integral, then they missed out on the entire marks. But basically, this is actually a lot simpler than obviously a lot simpler than those students thought. And before I go that, I should say that obviously, if I was explaining this in class, I'd leave pauses for students to think about it and so on. But obviously, you can do that yourself by using the pause button or whatever. The simple explanation is that to do this integral, you need a trigonometrical identity. And the one you need is sec squared x equals 1 plus tan squared x. And from there on, sec squared is part of a standard derivative. It's the derivative of tan x. Derivative of tan x equals sec squared x, and that's all you need to know really. It's worth noting though that this particular integral that this particular identity that I've just mentioned can be derived fairly easily. You take the very basic identity, sine squared x plus cos squared x equals 1, and you divide that through by cosine squared x. And obviously you can get also another further identity by dividing the original identity through by sine squared x. It's worth noting along the way that quite a few students in the exam tried to use integration by parts. Now, it's worth noting that integration by parts, there is a certain strategy involved here. You obviously at the end of the day, you're going to end up with an integral on the right-hand side, if I can put it like that. You're going to get two parts, the second one of which is still an integral. And the general idea is you want this second integral to be one that you can actually integrate by definition. So if the original expression, say for example, had a log x in, then you would have it such that would be differentiated in the second term. So log x will go to 1x, and you would hope that 1x would cancel out with the other term, so you'd end up with an integral that you could actually integrate. If it was an x term, if you had no log x term and you tried an x term, then that x term would differentiate to a constant, and likewise the integral would hopefully be manageable. If it was an x squared term, then you would integrate by parts once, and you'd have an integral with an x term in. You'd then integrate that again by parts, and hopefully you would end up with an integral eventually that you could integrate. That's the general strategy of integration by parts, to end up with a nice little integral at the end of the day, which you can actually integrate. The obvious way that you can play around with integration by parts with respect to trigonometrical functions, if you've got an expression like sine x cos x or something along those lines, if you integrate it by parts twice, at the end of the day you end up with an integral with something like some number times the integral of sine x or cos x or whatever expression it was you started out with. So you could then do a bit of a trick to actually solve that integral. You could send the integral at the right hand side over to the left hand side and process it that way. Excuse me. But when you think about it, you can't actually work that with a tangent. So that's the essence. If you say, okay, tan squared, I'll try that by integration by parts. It's not going to work. You're not going to end up with an integral at the end of the day with just one term in which you can integrate. Likewise, you're not going to be able to have this sort of manipulation where you can use this sort of trick that I've just mentioned for trigonometrical functions. So again, that's something to bear in mind, that when you use integration by parts, there is a purpose behind it. So just don't operate it. Just don't attempt to use it blindly. Anyway, cheers for now.